Our next speaker is Dimitri Mawet. He's a professor of astronomy here at Caltech and a recognized technologist as well. What I really appreciate about Dimitri is he really does play in these two areas of astronomy as well as technology that enables new methods and techniques. So his research focuses on high contrast imaging and spectroscopy of exoplanets with cutting-edge developments in coronagraphy and null interferometry. Dimitri's work is crucial for improving our ability to observe distant planetary systems. So with no further ado, Dimitri.
The microphone. All right, thank you, Kent, and thank you for asking me to give you a short course on high contrast imaging of exoplanets. So in the background, there's an image there that was taken with the James Webb Space Telescope of an exoplanet, which is a large, young, warm, bright gas giant planet, so relatively easy to see. And it was enabled by coronagraphy, a technique that we'll describe. And the element that allowed us to take a picture like this, the coronagraph itself, was built many years ago. That's something to remind us that what we are discussing this week is relevant to HWO, and I don't think we can extrapolate too much into the future what the technology will be able to do in 20 years when the mission flies, because some of these technology developments need to be frozen very soon. I say that because right about the time when James Webb froze its technologies, I had come up with a new concept that didn't make it, and it was 20 years ago, okay? And we know the observatory just launched a few years ago, so there's a huge gap between the technologies that can be infused into a space mission because it takes a long time to build, integrate these spacecrafts. And NASA like to have things that are well developed a decade at least before the mission actually launches. So just as a friendly reminder. That being said, I wish I'd been invited to a workshop like this 20 years ago when I learned about metasurfaces, even though at the time they were not called metasurfaces. At least it was not a popular term in the scientific literature. We call them zero-order gratings, diffractive optical elements, spatially variant half-wave plates, and so forth. So I understand today that those now fall into the category of metasurfaces and the buzzword that it became. Let's go back to exoplanets. So, in short, we today know of more than 5,000 exoplanets, so planets orbiting stars other than our sun. And what is surprising is not so much the number, but the variety of planet types that have been discovered so far, all the way from gas giants like our Jupiter down to small planets like the Earth, going across all possible planet types that we encounter in our solar system, the ice giants, some mini-Neptunes, but also new types of planets that do not exist in our solar system. We call them the mini-Neptunes or the super-Earth. And those are really surprising discoveries and lessons from, humbling lessons, I should say, about what the universe and nature can actually create. So our solar system is fairly unique. We haven't found anything like it so far. And that is in part due to the techniques we've been using for the past 30 years or so. So each one of the techniques that I will describe very briefly here are biased towards some planet types just because of the limitations of the technologies and the techniques itself. So by far the most successful technique by the numbers is the transit technique, where we just monitor the brightness of a star, so photometrically, over time, and look for a periodic dimming of the planet light, which indicates that something is orbiting around the star, so hence the periodicity, and is blocking the light that we receive from the star. So we don't see, we don't take a picture of the planet crossing the disk of the star, but we just monitor its brightness over time. That technique has been incredibly successful, responsible for thousands of these discoveries, and in part because of a space mission called Kepler that was launched in 2009 and monitored a field of 150,000 stars for a few years monitoring their brightness over time and then discovering thousands of exoplanets in the way. So the other technique that is very successful, and it actually is the first one that enabled the discovery of exoplanets in 1995, is the radial velocity technique. Here the technique is completely different. We take a spectrum, high-resolution spectrum of the star, and we look for the Doppler shift of the stellar lines as a function of time as the star is responding to the gravitational tug of the planet pulling on it. So that technique has been incredibly successful as well. One thing that the technique is really good at is to measure the mass of the planet. While the transit technique can measure the radius of the planet, the radial velocity technique can, because it relies on Newtonian dynamics, it can measure the mass of the planet. So when those two are combined, we can measure the bulk density of a planet and try to model its interior. So there are other techniques like that I won't mention. There's astrometry, there's microlensing, and then finally direct imaging. And you see by the numbers, it's only responsible for about 1% of all discoveries so far. And the reason being that direct imaging of exoplanets is really, really hard. So this is one of our best picture of Sirius. You can see Sirius in the night sky with the naked eye. Sirius is actually a binary. It's orbited by a white dwarf, Sirius B. And the contrast ratio between Sirius A and Sirius B is about 10,000 to 1. So Sirius B is 10,000 times fainter than Sirius A. And it's a few arcseconds away, which is a lot for a space telescope like Hubble, which allowed us to take this picture. So this is a $1 billion picture, our best picture of Sirius. And yet you see that if I bring Sirius B, right, I'm God and I can move stars around on the fly. If I bring it in the habitable zone of Sirius A, well, potentially a planet like the Earth could reside, you see from this image alone that it would be impossible to see, would be completely lost in the diffraction and scattering induced by Sirius A going and the wavefront propagating through our instruments, like the Hubble Space Telescope, creating this mess of light that's splashing everywhere in the focal plane on your detector, again, due to diffraction and scattering from imperfections in the optical system. So I'll show you that for exoplanets, the situation is worse than Sirius A and B because the contrast ratios involved are much, much larger, and the separation, as you can see here with the circle, are much smaller. So we can describe the light we would receive from an exoplanet as a function of two terms. The first one is the reflected light term. So the light from a planet is the light from the star reflected off from the atmosphere or the surface of a planet. It's proportional to the ratio of the planet's size to the distance to its host stars squared, times the luminosity of the star, because it reflects light from the star, a phase function, phi, which depends on the orbit and when you look at the planet along its orbit. And then this factor A, which is the albedo, or the reflectivity of the planet's surface or atmosphere. That's the reflected light term. The second one is the thermal emission, right? Planets have a finite temperature, thank goodness, and so they emit light mostly in infrared, but that depends on the temperature. So we have the opacity, or the emissivity here, kappa, which is a function of wavelengths. We have the blackbody function of the temperature of the planet. And then the last factor there is the size of the planet itself. So two terms, none of them are great. They are completely overwhelmed by the star, which is much hotter, much larger, and orders of magnitude brighter. So the light from the star completely overwhelms the light from the planet, either in the reflected light regime or in infrared thermal emission regime. So the typical contrast ratios one has to deal with range from about 10,000 to 1 in the most optimistic, easiest cases of self-luminous gas giant planets, the size of our Jupiter, but much warmer because it's young and still contracting and releasing that energy in the form of radiation, to 10 to the minus 10, so one part in 10 billion, which is the reflected light that we would receive from the equivalent of the Earth orbiting a star like our Sun. So that contrast ratio is compounded by the fact that those planets are close, angularly speaking, to their star. So 1 astronomical unit, the distance from the sun to the Earth at 10 parsec, which is about 30 light years away, is only an angle of 0.1 arcsecond. Okay, so that's the tiny angle. So that's the challenge really for exoplanet imaging. And the ultimate goal of the field is to be able to take a picture of an Earth-like planet. And so the contrast ratio between the star and an Earth-like planet is this 10 to the negative 10 number that you will see over and over again this week. So that really is the challenge. And being able to image that faint an object right next to a very bright one is really what's been driving the field of exoplanet imaging for the past 20 years or more. So why do we care about taking pictures of exoplanets? I mean, those are maybe good for press releases, but really the point here is to try to isolate the signal, so the reflected light and the thermal emission signal from an exoplanet, so that we can characterize it and learn something about it. So it's not just about taking pictures, it's about isolating a signal from a faint signal from a bright one right next to it so that we can make measurements. So the measurements are positions, so we call that astrometry, which we use to characterize the orbit. So if we measure the position of a planet a long time, we can then trace the orbit and figure out what the orbital parameters are. What is the separation to the star? Is it an eccentric orbit? Is it going to go much closer to the star than what we actually see right now? In which case, the planet would not perhaps be habitable. We also can do photometric measurements over multiple wavelengths. And through modeling and a lot of theory, we can infer some bulk parameters like the temperature, the mass, the radius, the albedo of the planet. And then finally, maybe the most powerful one is spectroscopy. So we can disperse the light and try to look for the fingerprints of molecules that are present in the atmosphere of the planet. So I show you some real images of exoplanets. So some of you may not have seen some of those before. They are pretty ugly, I would say. So we have here some of the famous ones we've imaged. And I just want to remind you that what we see is a point source, right? Our telescopes are not large enough by any means to actually resolve the surface of these objects. So we see them as point sources isolated from the central star. So in each one of these images, you see the residuals from the central object, which is much brighter, in this case about 10,000 to 100,000 times brighter than those planets, which are resolved as point sources here in the image. So when you see pictures of exoplanets like on the poster, they are always artistic renditions. So this is one of the latest one that was discovered by the James Webb Space Telescope, resolved in the infrared by the MIRI instrument. So what we see here in all of these images is the thermal emission term that I discussed before, because these planets, most of them, pretty much all of them imaged so far, are glowing in infrared because they are still warm. This one, in particular, is the coldest one ever imaged. Its temperature is only a few hundred degrees Kelvin, compared to the ones I showed before, which were 1,000 or so degree Kelvin. So, as I said before, this is now a real movie of this exoplanet system I showed with 4 planets. As we image these planets over time, we can actually trace their orbit. So this is one of the first things we can do with direct imaging. So we can also try to characterize their atmospheres using spectroscopy. So this is all the highlighted dots here are the planets of all the planets known so far that have been characterized. So there's only a tiny fraction of exoplanets discovered so far, or out of the close to 6,000 exoplanets, only a couple hundred have been characterized spectroscopically for the transiting cases and for the direct image cases. But with direct imaging, we can get data like this. And so this is a boring plot. This is a spectrum. This is one of the best spectrum of an exoplanet ever taken, again with the James Webb Space Telescope. So we get a spectrum in the infrared from about 1 micron all the way to 15 micron continuous. And from this spectrum, and this is not noise here, all of these features are real features coming from molecules present in the atmosphere of a planet. And so we are pretty good at recognizing these patterns and figuring out what they mean for the pressure temperature profile and the abundances of various elements. Here we've detected water, carbon monoxide, and methane, and those are amazing data sets that theorists can use to then refine our understanding of exoplanet atmospheres and put that in context with what we know about our own solar system and planet formation. So our really driving goals for the field is to be able one day to take a spectrum of another Earth-sized planet. So we know those exist, we've detected them, but we haven't been able to take a spectrum of one yet. And so if we compare a spectrum of small planets in our solar system, this is Venus, Mars, and the Earth, which have roughly the same size, we see that the spectrum of the Earth is very different from the other planets because it has life. All these features you see that are different from Venus and Mars are due to the presence of life at the surface of the Earth. So that's really something that we are hoping to learn with observatories like the Habitable Worlds Observatory. So of course, we're looking for signs of life as we know it, as the Earth tells us how it is, but we're also smart enough to try to be able to detect signs of life as it was before through the Earth history. So a lot of theorists, some of them actually now in leading positions on the HWO observatory team, have done this extrapolation to the Proterozoic Earth, the Archean Earth, and try to understand what the spectrum of the Earth would have looked like back in the days. So the abundance of various elements, so biomarkers that are showing us that there is life on the planet, have been changing over time, and we're trying to capture all these possibilities to design the HWO mission around. All right, so I'll switch gear a little bit and talk more about the techniques. So now that we have our goal, let's see how we can get there eventually. So to be able to take an image of a planet, we need 4 ingredients. So we need to control the wavefront. We need to suppress the starlight so we can overcome this huge contrast ratio. We need a strategy to observe the object. That means perhaps slewing the telescope to another star so we can have a reference without the planet and be able to subtract that reference image from the target image. And it is necessary because these 2 ingredients alone are not sufficient to reach these high contrasts. And then we need algorithms to be able to treat the data, to post-process it, to reveal the planets and make all these measurements. So let's start with the first one, wavefront control. Oh, sorry, there's a movie here. So this is an animation that was done a few years ago by colleagues at the European Southern Observatory, showing what happens to the wavefront when they propagate through mostly our Earth atmosphere and our telescopes. From plane waves, they become corrugated, and it is due to the fact that the refractive index of the air in our Earth atmosphere is not 1 exactly, and it changes over time, which corrugates the wavefront and distorts our images. So if you look closely, it's a mess. So there's no way we can take any telescope on Earth and put a coronagraph behind it and try to image an exoplanet. We need to control the wavefront. That is true on Earth. This is really, really true on Earth because of our Earth atmosphere, but it's also true in space where the distortions are not coming from the presence of air, but from tiny imperfections in all the optics that light bounces off. And those disturbances, they change pretty quickly down here because the air is turbulent. But in space, they change over time as well because the observatory is subject to all kinds of changes. When the telescope slews, the spacecraft slews to another star, the sun exposure is changing, and so the thermal gradient propagating through the spacecraft is affecting all the optics, changing the wavefront. So we have something, though, a tool to combat these changes. And that is a bit of history here. That tool is now called adaptive optics or wavefront control, but the first idea came about in 1953. Horace Babcock said, if we had the means of continually measuring the deviation of rays so as to correct the aberration pattern, we could expect to compensate for any imperfection in the optical figure. So Horace Babcock was a Caltech undergrad and then went to the UC Berkeley for his thesis and became later on the Palomar Observatory director. And he laid out the blueprints of a technique called adaptive optics, or more generally speaking, wavefront control in astronomy, which is that we measure the wavefront with a sensor. We call that the wavefront sensor, very boring. And then we feed back that measurement to a mirror that we can deform. We call that, again, boring, deformable mirror. So these mirrors are tiny. I don't know if you've seen one. Maybe I can go grab one in my lab later on to show you, but those mirrors are really, really small. They are a few inches in diameter maximum. A lot of students in my classes get confused. Sometimes they think that we actually move or deform the primary mirror of the telescope. We can do that, but not fast enough, not precisely enough for the goals of direct imaging of exoplanets. And actually, a lot of modern telescopes can actuate their mirror, primary mirror, but they do that over very long time scales. So this is what adaptive optics can do for you. So this is an image of the galactic center. The first one that you see is seeing limited without an adaptive optics system. This is taken with our most powerful ground-based telescope, the Keck telescope in Hawaii, 10 meters in diameter. It's gigantic. But without adaptive optics, it's no better for imaging than your small backyard telescope toy that you buy at Walmart. So that's because of turbulence in our atmosphere and those corrugated wavefronts that come into your instrument and your camera. With adaptive optics, we measure the wavefront in real time. We feed back that measurement to a mirror, the deformable mirror, so that we can correct for these imperfections in quasi-real time. And then we restore the diffraction limit of our telescope. So that would be step number one. That's tool number one for imaging planets. Now that we've restored the theoretical diffraction limit of our telescope, now we can try to see if we can extinguish or suppress the light from the central object. One way to do that is to use the moon, although not very convenient. The moon is a very good coronagraph, and actually the word coronagraph comes from this first application, which is to study the solar corona. And so this is here a picture of the corona of the sun taken during a total eclipse of the sun by the moon. The moon is really, really good. The corona contrast to the solar disk is about 10⁻⁷, so 10 million to 1. Okay? It's even it's so good that you can resolve stars in the background. Right? This is a spectacular image of the solar corona. Maybe some of you have experienced this in the past few months with the last solar eclipse. So to study the solar corona, a century ago, solar physicists were forced to travel the world and chase solar eclipses, and they only had a few minutes to take their measurements. Bernard Leo, a French astronomer / instrumentalist, was perhaps tired of traveling the world chasing solar corona, so he invented a device, an instrument called a coronagraph, to mimic the effect of the total eclipse of the sun. And so his instrument is very simple. It's a telescope. So there's an entrance lens, could be a mirror, focusing the light onto a primary focal plane where he puts an occulting spot that is roughly the angular size of the sun, so blocking the light from the solar disk. And then because Bernard Leo understood diffraction and the wave nature of light, he saw that it was not enough to do that because light would spill around the edges and then you wouldn't really get high contrast in the final photographic plate. So he introduced a field length C and a diaphragm D so that we could control the effect of diffraction around the edges of the occulting spot. It worked really, really well. And this concept from close to 100 years ago is still the basis for modern coronagraphy. So coronagraphy is a tool. It's a tool to create images in a high contrast scene when you're interested in a faint object. And Bernard Leo did that very successfully. Behind his coronagraph, he put spectrographs, he put polarimeters, so he could study his favorite astronomical object, which is the solar corona. And those are pictures of the solar corona and coronal mass ejections that Bernard Leo took himself in the 1930s. Solar coronagraphs are extremely useful. They are everywhere in the world. In space, we have observatories monitoring the sun 24/7. Pretty much all of them are equipped with coronagraphs, solar coronagraphs. This here just a movie from Soho, which has one type of coronagraphs, which is close to Leo's original ID, showing you how good these images are, and that we can see the stars in the background. So for about, I would say, 40 to 50 years, astronomers have been interested in using coronagraphs for other than studying the sun's corona. And so they've tried to apply this same technique to look for exoplanets around other stars and other objects in high contrast scenes. So now we're going to combine both a coronagraph and a wavefront control system. And I'll show you a short movie that was put together about 10 years ago at JPL for the Roman coronagraph instrument that actually has been delivered to Goddard and will launch in a couple of years. So we're going to start with the scene. So this is all CGI, of course. We have two exoplanets here. We have an Earth-like planet. We have a Jupiter-like planet. They are both orbiting the star that we see in the background. Like if you look at this scene from our vantage point on Earth, this system looks like any other star in the night sky. So there's no way to tell whether there are planets around them. So we point our telescope towards this star. The wavefront come in. So the wavefront will pick up any aberration in the optical system. So optics are never perfectly polished. Now we put our coronagraph at the focal plane there. So it's an occulting spot, maybe a bit fancier than Leo's original occulting spot. We have Leo's field lens and the diaphragm to control the diffraction. And then finally, we can focus everything on our final detector. So now that's for the star. The star is centered on the occulting spot. The planet light comes at an angle and goes through the same field lens, the diaphragm. Now we can take our image, increase the exposure time. The planets are nowhere to be seen. What we see here is scattered light from the central object, which completely overwhelms the planet light. So now we can use our deformable mirror. So we're going to push and pull on the surface to try to flatten the wavefront. And in the process of doing so, all these speckles of starlight are clearing up, revealing our 2-point sources in the image. Okay? All right, so let's go through a few definitions. So this week you'll hear a lot about some of these. So I wanted to make sure we were on the same page because there's sometimes a bit of confusion. So the flux ratio is the ratio of intensities between the unattenuated starlight and the planet light. So we talk about 10 minus 10. Oftentimes that refers to the flux ratio between an Earth-like planet and a Sun-like star. When we talk about raw contrast, it's different. It's actually how much we suppressed the starlight. The planet throughput through an optical system is how much of the photons from the planet have we actually saved all the way to the final detector. You'll be surprised to hear that after a modern coronagraph, oftentimes we only have a few percent efficiency collecting photons from the planet itself. So 90% of the light or more is being wasted in reflections, in lossy optics and whatnot. Although it's really important to try to do our best to conserve these photons as much as possible because that's where we'll be taking our information from. So we have a concept called the inner working angle, which is defining how close we can find planets to the star. So we want to work as close to the diffraction limit as possible. The formal definition is 50% of axis, transmission point. You'll see a few of these curves during the week. But just keep in mind that that doesn't mean that there's a hard cutoff at 50%. We can still see planets within the definition of the inner working angle. It's just that the transmission is going to be worse. The outer working angle is how far we can see a planet from the central star. That depends on the number of control elements in your adaptive optics / wavefront control system. So that defines the outer edge of what we call a dark hole, which is this high contrast region that we define in an image that extends from the inner working angle to the outer working angle. Bandwidth in this context is crucial. We talk about bandwidth here in terms of optical bandwidth for the filters we use to do our measurements, imaging, spectroscopy, astrometry, and so forth. So it's delta lambda over lambda. It's typically 10% to 20%. So that's something that I think is maybe a challenge for metasurface builders, as they oftentimes design their structures to be narrow band. Here in astronomy, we want to collect light over large bandwidth, so we can do all these measurements. And then finally, there's another one, which is the robustness of the coronagraph, how robust it is to optical aberration. So we want to build in some robustness in the coronagraph itself, excluding all active control we have over the wavefront, so that we make our life a little bit easier. So this is from the movie, the diagram of a typical coronagraph. So we have our telescope collecting light. There's a few folding optics here, reformatting optics. Then we have our first entrance pupil, a lens to focus the light in the focal plane, another lens that's from Leo himself, a field lens, and a diaphragm here, and finally a final lens to form an image, our final image. So the occulting spot is in the first plane here, the first focal plane. So this is just here the point spread function for a star at infinity. We occult the first few rings of the diffraction pattern, and then we put our field lens, reimage the pupil. What you see here at the edge of the pupil is the effect of diffraction around the edges of the occulting spot. And then we put a diaphragm, like Leo suggested 100 years ago, to try to cut out some of that diffraction, now concentrated around the edges of the pupil. So to describe a coronagraph like this, it's actually pretty simple. We use Fourier optics. And that's something that I'd like to discuss this week, is how we can interface tools to model metasurfaces, the microscopic scale, and the far field representation of a coronagraph using primarily Fourier optics. All right, so after the Leo step here, we've cut out the diffraction at the edge, and then you see the final result here, which is an attenuated version of the point spread function. So Leo coronagraph itself is not a great coronagraph. It leaves out a lot of diffraction at the end. So we'll show you a few more coronagraphs that are working better than Leo's coronagraph. So the planet light comes at an angle, it misses the occulting spot and propagates normally to the final focal plane. So pretty much all coronagraphs that we've come up over the past 20 years or so use the same original ID. The only variation between them is where we modify the wavefront dielectric field, either the entrance pupil, the focal plane mask, or even sometimes downstream in the Leo stop. So I told you Leo's coronagraph is not the best coronagraph, yet it has the record of contrast ever achieved in the laboratory. So why is that? So it's kind of puzzling. If you do a Fourier optics simulation of a Leo coronagraph through a standard coronagraph layout like I just showed, clearly you see there's 1% residuals in the end. Yet it has achieved close to 10⁻10 raw contrast in the lab. So what would be happening here? What's the magic? The magic is that this experiment, and pretty much all high contrast imaging experiments today, incorporate these deformable mirrors so that we can modify the wavefront, right? So here what you see is the effect of an occulting spot like Leo's coronagraph and the addition of active wavefront control. So that is to say that the deformable mirror in this experiment are doing most of the work, okay? And that's an issue, because when you use the active wavefront control system to deal with static diffraction, you're actually losing a lot of mileage on your ability to then correct for the other kinds of aberrations in the system. So this is a great experiment, but this is done with a coronagraph that is suboptimal, because in the process of doing that, we've actually used a lot of our reserves to actually kill diffraction. And we have coronagraph concepts that are actually much more efficient at killing diffraction, that are not taxing so much on the wavefront control system to do all the work, okay? So I said in my description for the course that I would show a family tree of coronagraphs. So there are many, many, many different concepts. Some of them were described a long time ago by Olivier Guillon. They all he showed their performance in terms of off-axis throughput, so how much of the planet light they transmit for various angular separations. So I won't go over the details of this. Maybe we'll have plenty of time to discuss some of those this week. Just to say that there are too many concepts. A lot of them are fairly advanced and well demonstrated, but I think the absolute truth comes from experimental validation. So this is a comparison of, on a level playing field of the most successful coronagraph concepts to date. It is not complete. There are many that are very promising that are being demonstrated as we speak. But really, what is key is this reality check in the lab, right? So we can come up with all kinds of crazy ideas, but really the final check is what we can achieve in the lab, what we can manufacture, and when we can demonstrate and understand from a modeling standpoint as well, and from a physics standpoint as well. All right, so I only have 2 minutes. This is great because this is about vortex chronograph, which is one of the interesting concepts out there. Maybe not the best, very best, but one of the most interesting in terms of its trade-off between various performance metrics I mentioned before. And this is currently being considered as one of the top 3 or 4 choices for the Habitable World Observatory. It's by no means a final choice for it, but it's currently being studied in a lot of details. So the vortex chronograph imparts an helical phase distribution on the point spread function, which we showed almost 20 years ago, produces a complete cancellation of the starlight, a perfect rejection. So contrary to Leo's chronograph, it does actually kill all of the light from the diffraction pattern. So one of the difficulties with this chronograph has been to actually make it. There are multiple options to do that, and we've investigated a lot, and there are more and more that are being investigated every day. So there is a scalar using longitudinal phase scalar vortex chronographs that are currently studied in detail. So this is a bit of a newer, actually it was done originally 20 years ago, but dropped for some reason. But now, recently with Metasurfaces, we think that this scalar vortex concept has a lot of promise for solving this polarization dependency of the other approach that we've been studying for longer, which is the vector vortex chronograph. So I won't go into the details here. There's 2 different families of vortex chronographs, scalar and vector. They use very different technologies for fabrication, from Metasurfaces to traditional stepped vortex profiles to liquid crystal retarders, sub-wavelength gratings, and liquid crystal vortex grating masks as well. Very briefly, so this is a representation of the typical space-based chronograph, now putting all the pieces together. So we have deformable mirrors, we have focal plane masks, we have Leo stops, we have filters, we have cameras. And something I haven't really talked about yet is the integration of the wavefront sensing and control aspects with the chronograph. So originally, we were thinking of these 2 things as separate. So there's the adaptive optics system, and then we slap a chronograph behind it. But for space-based applications, now these 2 functions are being integrated into a single instrument and thought of holistically. And I want to mention the work that was done at JPL for the Roman chronograph, which is this technology demonstrator flying on board the Roman Space Telescope in a couple of years. And that instrument, as I said before, has been delivered to Goddard and is being integrated to the spacecraft as we speak. And that chronograph has all the ingredients that we would want into the HWO chronograph. So it has the deformable mirror, the focal plane masks, and then these active control loops between the final camera and then lower order wavefront sensors and various correcting elements like the DM, fast steering mirrors, and so forth. And I think where Metasurfaces can play a great role is into helping us integrate these various optical functions into this holistic, high contrast imaging instrument. All right, so I'll finish on this. Habitable Worlds Observatory, 2040 launch, 6 meter, perhaps off-axis, hopefully off-axis, covering the optical to the near-infrared. A chronograph will be on board, which will be able to dig a dark hole to resolve planets, take their spectra. The challenge at 10-10, and keep that number in mind, is that we need OPD control at the 10 picometer level. I don't want to scare anyone off, but this is what we have to work with. okay? That doesn't mean that your metasurface has to be controlled at the 10 picometer level, but as a whole, with everything folded in, including active wavefront control, we need to arrive at that number. This is my last slide. So I think exquisite phase and amplitude control is needed for high contrast imaging of Earth-like planets. I think there are many areas where metasurface can help: coronagraph, focal plane masks, beam shaping optics, wavefront sensing elements, and how we integrate them into the coronagraph, and finally polarization control. And I'll stop here.